Hi, this is Marc Roth, and this is Mathematics for Social Justice. Today we'll be talking about the harmonic mean again, and also some of the things that it's related to, such as completing the square, hand calculating square roots, and Pythagorean triangles. In previous videos, we came up with an alternative formula for the harmonic mean, and today I want to show you how to use it with students. And I want to avoid the math wars. I'm not going to take a position that this is one way to teach, and it's really the only good way to teach, and forget about this other way to teach. I don't want to get involved with the math wars. So in other words, some people think the only way to teach is to sit students in groups of 4 and have them work collaboratively on problem solving. Other people think individualize and have the students do drill and until they master a subject and then move on. I'm going to talk about how you can use the latter method, but not with empty drill, with drill that has some meaning to it. And I'm not trying to say this is the only way you should teach. I'm just saying that there's students that need to catch up, and those students can be aided by an individualized program that has drill, but hopefully not empty drill. So the harmonic mean can lead to some practice with fractions. So I want to have an even number of spaces. Starting with 4 spaces. And so to find the harmonic mean, first you can label this A and this B and this M in the middle. And then you choose a whole number here and here, where this one is less than this one. In other words, A is less than B, and A and B are both elements of the positive integers. And A plus B is equal to the number of spaces. So I want 1 to be less than 3. 1 plus 3 is 4 because there's 4 spaces. And they're both whole numbers, or positive integers. So that's a step. Label lowercase a on the left, lowercase b on the right, lowercase m in the middle. And then choose these 2 numbers that add up to the number of spaces. And then the next thing you do is look at this number, whatever it is, you go that far over and write h. And it will be the harmonic mean of 1 and 3. So now to find the values of these other points on the number line, first you find how long each space is. And you do that by doing b minus a over b plus a. B minus a is how far it is from A to B, and B plus A is the number of spaces. So if this was a bicycle trip going from the A mile mark to the B mile mark, this would be the length of the trip divided by the number of spaces. It'll tell you how long each space is. So in this case, it's 3 minus 1 over 3 plus 1, which is 2 over 4, which is 1 over 2. So it's 1.5, 2, 2.5. So the student can fill that in and then do a multiplication. M times h. Well, m times h is 2 times 1.5. 2 times 1.5 is 3. And notice that a times b is also 3. So we're verifying that a times b equals m times h. So again, this can be a discovery process. We don't have to tell them in advance that a times b equals m times h. They can discover, after doing a few of these, that, oh, m times h equals a times b. But in the meantime, the students are just getting fraction practice. In the pedagogy, we don't want to bore the students, so we don't want to give them, too much. But we can monitor how many problems we want to give them. And if they start to get bored, we stop. But some students will need to do several before they stop asking for help. So we go from 4 spaces to 6 spaces and label this A and B and M in the middle. And now we have a choice. We have 6 spaces, so we can go 1 and 5, or we can go 2 and 4. Well, let's start with 1 and 5. And since this is 1, we go one space over and write h. Now again, we have to go b minus a over b plus a to get the length of the space. So b minus a over b plus a is equal to 5 minus 1 over 5 plus 1, which is equal to 4 over 6, which is equal to 2/3. Okay, in my teaching, I often had students that had trouble adding by 2/3. So I gave them a visual aid. It's called the chewing gum method. This tells you how many pieces of gum. So it's going to be 5 pieces of gum. So I make a rectangle. And for 5 pieces of gum, I need 4 more horizontal lines. So I have, here are my gums, 1, 2, 3, 4, and 5. It's ABC gum. It's already been chewed. This tells you how many pieces of gum have already been chewed. So it's 1 piece of gum's already been chewed. Next, we look at this fraction, 2/3. 3 tells you how many columns. So we need 2 vertical lines in the interior, and 2 tells you how many letters in a row that are the same. So we could go X and X, 2 letters the same in a row. And then we switch letters to O and O. And when we had the 2 X's, it was 1 piece of gum and 2 parts out of 3 of another piece of gum. So 1 2/3. Then we add the 2 O's, now it's 2 pieces of gum and 1 part out of 3 of another piece of gum, so it's 2 1/3. And then which is 3 pieces of gum, 2 O's, 3 2/3, and 4 1/3. Okay. So this visual aid has helped my students fill in the number line. So finally, they go m times h. 3 times 1 2/3. So that would be 3 times, it's the bottom times the side plus the top. 3 times 1 is 3 plus 2 is 5. The 3's cancel and we get 5. And notice that 5 is the same as 1 times 5. So again, m times h equals a times b. The next example would be same number of spaces. This time 2 and 4. And this is still A, this is still B, this is still M in the middle. And for H, we go over 2 spaces. And to find the value of each space, again, it's B minus A over B plus A equals 4 minus 2 over 4 plus 2 equals 2, 6 equals 1/3. Well, adding by 1/3 is easy. You don't need the chewing gum method. So it's 2 1/3, 2 2/3, 3 1/3, 3 2/3. So again, m times h equals 3 times 2 2/3. So that's equal to 3 times 2 is 6 plus 2 is 8 over 3. The 3's cancel and we get 8. So m times h equals 8, and 2 times 4, which is 8 times b, equals 8. So once again, 8 times b equals m times h. Okay, so for teachers who want to give their students a challenge, this is a good problem. When can you have A and B and M and H all whole numbers? Because H is often not a whole number. So for example, if you have 2 and 6, halfway between 2 and 6 is 4, and 4 times 3 is the same as 2 times 6. So what are other examples where this number is a whole number and not a mixed number. So that's a good problem to give to your students, and there's some easy ways to solve it, but there's also some difficulty to the problem if they can't come up with a shortcut. So then, if you like to sit your students in groups of 4 and give them a challenging problem, this would be a challenging problem. But it has an easy solution to it because the harmonic mean is homogeneous. So for example, if you have, we already looked at the case where we had 1 and 3, and we had 2 and 1.5. And this was M, and this was H, and A and B. If we times everything by M, so we end up with M times A, M times B, M squared, and MH. Well, MH is equal to AB, and A times B is a whole number times a whole number. So we're going to get a whole number. So if we just, now M is 2. So if we just times all these things by 2, instead of having 1 and 3, we're going to have 2 and 6. And that'll be 4, and that'll be 3. So that's the one we just talked about before. But we can do that many times. So for example, if we have 1 and 5, this was 1 2/3, if you remember. And this was 3. If we times everything by M, it's going to become 3. 5/3 becomes 5. 3 times 3 is 9. And 3 times 5 is 15. So again, 3 times 15 is 45. 5 times 9 is 45. And this will be a whole number. So 5 will be the harmonic mean of 3 and 15. And the harmonic mean times the arithmetic mean will be equal to the product of the two numbers. So we end up getting an interesting pattern. The square number 4, and then we subtract the first square number, which is 1. So we subtract 1 and get 3. And then to 4, we add the square root. Square root of 4 is 2, so we add 2 and get 6. And we subtract the square root and get 2. We can do that again. Move to the next square number. We're going to use the next square number twice. So first, we subtract the first square number, which is 1. And we subtract the second square number, which is 4. Then we add the square root, which is 3. And we subtract the square root from 9 and get 6. And 6 times 12 is 72, and 8 times 9 is 72. And 9 is the arithmetic mean of 6 and 12. So here we're going to add twice the square root. So 2 times 3 is 6. We're adding 6 and getting 15, subtracting 6 and getting 3. So again, 5 will be the square root of 3 and 15. And again, 3 times 15 is 45, 5 times 9 is 45, and 9 is the arithmetic mean of 3 and 15. So moving on to 16. First, we subtract the first square number. Then we subtract 4, the next square number. Then we subtract the next square number, 9. Here, we add the square root and subtract the square root. Here, we add twice the square root, which is adding 8, and subtracting 8. And 8 times 24 will be the same as 12 times 16. And here we subtract 3 times the square root, which means we're subtracting 4 3 times. So we're subtracting 12 and getting 4, adding 12 and getting 28. So I was able to come up with a proof, which I won't do for you, but we're going to consider if we get all the primitive solutions this way. So this is a primitive solution because there's no number that goes evenly into all these numbers. There's no integer that goes evenly into all these numbers. So this is a primitive solution. This one is also primitive. This one is not. So this one is not primitive. Because we can divide by 4, 4, 4, and 4. And when we do that, we get the top result. But the question is, do you get all the primitives by using this pattern? And I was able to prove that you do. Okay, so next we're going to use the harmonic mean, or actually an extended version of the harmonic mean, to exploit a formula that I used in the first version of the harmonic mean. And you'll see how easy this makes the problem. So suppose this is the unit square. So it's 1 on each side. It doesn't look great, does it? Let me make this go down a little further. Okay, so suppose we have this diagonal, and we have another diagonal that only goes to here. Suppose this is 1/3, and this is 2/3. And we want to know this area. So we can make use of a formula that I gave you last time. This time h stands for height, okay? So it's this height here. So the height will be equal to a times b times alpha plus beta minus 1 divided by a times beta plus b times alpha. So a is the height of this post sticking out of the ground. So this is a. So a will be equal to 1, because this is the unit square. And this is b. So b is equal to a. They're both equal to 1. And if you look at this distance is going to be beta, which is going to be also 1. But alpha is not 1. Alpha is only 2/3. So if we plug in these numbers into this formula, we're going to get this height. Now we could also get this height with linear algebra, but using this formula should be a little quicker, slightly quicker. So a and b are both 1, so we have 1 times 1. Alpha is 2/3, so we have 2/3. Beta is 1 and minus 1. We're timesing 1 times beta, which is 1 times 1, plus b, which is 1, times alpha, which is 2/3. Now, here the 1 and the minus 1 cancel. We end up with 2/3 in the numerator, and the denominator will be 1 and 2/3. This turns out to be 2/3 over 5/3 times by 3 and cancel, and we get 2/5. So this is supposed to be 2/5 of the way up. That looks about right. H equals 2/5. Okay, so now to finish the problem, we know the height is 2/5. So the area of the triangle is 1/2 base times height. So the base is 2/3, so it's 1/2 of 2/3 times the height, which is 2/5. So we can cancel 2's. We end up with 2/15. So this area of this triangle is 2/15 of this unit square. So this is going to be equal to 1/2. down below this diagonal. So we just have to go 1/2 and subtract 2/15. So I can use the zip, zip, zip method, go zip, zip, zip. So it's going to be 15 minus 4 over 30, which is 11/30. And that's definitely less than half. So the area of this quadrilateral is 11/30. And that's the answer. Okay, now we're going to review something that we did in our very first video, which was completing the square backwards. So this is a Cuisenaire rod lesson that I discovered many years ago. So if you're not familiar with the Cuisenaire rods, they're either wooden or plastic, and their normal size is centimeter lengths and 1 centimeter widths. So I prefer the wooden ones, and so this would be 3 centimeters by 1 centimeter. So I would put this on the table in front of a student, and then I would tell the student, take 4 red rods and 1 white rod and cover this up on the table. So one way they might do it is like this. I'm not covering it up, but and they would, I'm not sure you can see it, but I have a white piece. And you put a white piece right there. So these two things have the same size. But then I said, well, look, you got white in the corner, and you can rotate this and get white in any corner. Can you put these blocks on top of here a different way, where white's not in the corner, but somewhere else? So that's the only other way to do it. You can't put white in the middle of the side. It has to either be in the middle or in a corner. So then I can remove this, and I say, now notice that the reds wrap around the white in an interesting way. Can you find 4 rods of one color to wrap tightly around this to make a bigger square? And there are colors that won't work. For example, this color won't work. If you try to do it, you're going to be missing corners. You have to get all the way around with no missing corners. So the size that works is purple. And then I say, can you keep on going? Can you make another layer? Find 4 rods of one color to wrap tightly around this square to make a bigger square. One time I was teaching high school, and I was teaching, I guess what you would say, not the first track, but the second track. And I had trouble getting all the students to fully pay attention. But when I did this with the hands-on activity, every student was paying attention and interested, as far as I could tell. And finally, there's one more layer they can make. So then I tell the students, okay, we're going to need this later. Don't destroy it. But we're going to start making a new structure. This will be the core of a new structure. And you ask a student, find 4 rods of one color to wrap tightly around this rectangle to make a bigger rectangle. And sometimes people get stumped for a while because it's slightly different principle. Here they're going like one past, and here they're not. So they have to go like this. So if a student gets stumped for a bit, I don't help them. I just say, take your time. They figure it out. And then I keep asking them to make more layers. And at this point, I ask them, suppose you have many little white squares. Actually, in 3 dimensions, it would be little white cubes. So suppose you covered up this whole structure with white cubes. Would you, and also this one, would you guess it would take more white cubes to cover up this square or this rectangle? And they might venture a guess. I said, but now I'd like you to figure out exactly, I want you to figure out exactly how many whites it takes to cover up this square and exactly how many whites it takes to cover up this square. Now, if they get stuck, I give them a hint. I said, well, it takes exactly the same number of whites to cover up every color. So, for example, it takes 10 whites to cover an orange, you know, and it takes the same number of whites to cover up each purple. So some of them proceed to, most of the students I taught did not use length times width. Most of the students that I taught did addition. They would find out it takes 40 to cover the 4 oranges, 32 to cover the four browns, and so forth. And then eventually they would get an answer for this, which is 121. And when they get an answer for this, it's 120. I guess I forgot to say, I actually asked them to guess which one would take more. And sometimes they say this one, sometimes they say this one. Well, check your guess and find out exactly how many whites it takes to cover up this, and find out exactly how many whites it takes to cover up this. And so eventually they get 121 and 120. And then I say, okay, we'll peel off a layer. Now do it again. Find how many whites it takes to cover up this, and find how many whites it takes to cover up this. The students end up making a table on a piece of paper. So for the square, their first result was 121. And for the rectangle, it was 120. And so then when they stripped off the outer layer, they got 81 and 80. When they stripped off the brown, they got 49 and 48. They stripped off the dark green, they had 25 and 24. Okay? And we'll come back to these numbers later. So then I asked the student to make a companion structure if they're advanced. If they're not advanced, I give them the core. So this will be the core of the new rectangle. This will be the core of the new square. So again, they're going to find 4 rods of one color that wrap tightly around the square to make a bigger square. They're going to find 4 rods of one color that wrap tightly around this rectangle to make a bigger rectangle. These are the second set of structures that the student makes. So after the students make both structures, they end up getting interleaving results. So we get 121, 81, 49, and 25 for one structure. The outside layer was orange, the outside layer was brown, and then dark green, and then purple. And then for the other structure, the outside layer would be blue, and then black, and then yellow, and then light green. And this is for the square, and this is for the rectangle. And so then I give them scattered times tables on a separate sheet. So for example, they might see 7 times 9, written like that, and they have to place it somewhere in the chart. So they write 7 times 9. Or they might see 11 times 11, and they have to place that. So when they're all done, they get a pattern. Next, I asked them to explain the pattern. And so I might take them to the board individually and to test their understanding of the pattern. So I say, suppose I tell you the 17 times 17 is 289. What two numbers could you times together to give the answer 288? And see if they can come up with 16 times 18. And I say it's sort of like a sandwich, where 17 is the meat of the sandwich, and this is the lower piece of bread, and that's the upper piece of bread. So I might give them more than one example until they can understand. Or I might say, okay, suppose I tell you that 23 times 23 is 529. Okay, what would 22 times 24 be? So I'll test them on their understanding of the pattern. One of the things in these videos I've been trying to do is show you that the harmonic mean, completing the square, working with Pythagorean triangles, they're all kind of related topics, and they were all studied about the same time by ancient peoples. And so one more thing you can do is hand calculate a square root. So suppose I want to hand calculate the square root of 2. I can set it up like this. Again, where I have A and B, and M, and G, and H, where I have the arithmetic mean, geometric mean, and the harmonic mean. And so here I'm going to have the square root of A times B. And if A and B are close to each other, H and M will be even closer, and G will be in between. So I'm going to try to squeeze in on G. That's one way to calculate a square root. So for example, suppose I want A and B to be very close to M. So one way to do that is I know from a lot of years of doing math that 17 times 17 is 289, and 12 times 12 is 144, and that's almost twice as big as that. So if I take the fraction 17/12, it's going to be close to the square root of 2, because 17 times 17/12 times 17/12 is almost 2. So this is close to 2. It's a little bit bigger. So the square root of this is just 17/12. It's going to be, if I take the square root of both sides, I'm going to have 17/12, just a little bit bigger than the square root of 2. So I can put 17/12 here. It's already close to the square root of 2. So here I want A to be, when I times A and B, I want to get 2 on the nose. So I'm going to have 17 down here. So the 17s and 17s will cancel. And here I want 24. So if I times these two numbers, I get 2 exactly. And so here I'm going to calculate this by adding and dividing by 2. So here I'm going to go, so for that spot there, I want 24 17ths plus 17 12ths divided by 2. So my quick way of doing that is called the zip, zip, zip method. We go zip, zip, zip. 24 times 12 is twice as big as 12 times 12, so it's 288. And this happens to be just one bigger, 289. and times 17 times 12, that's going to be 170 plus 20, 190, 204. Over 2. So I can actually combine these two denominators and get, and if I add this and this, I'm going to get 577. I know that's 12 less than 300, 11 less than 300 together, 23 less than 600. And this is going to be 408. So I know this number is close to the square root of 2. Now suppose I only want 3 decimal digit accuracy after the decimal point. Well, I know from previous knowledge that the square root of 2 is approximately 1.414. It's easy to have that memorized because it's just 1414. So let me see if I get that if I do this division. Again, this is where the square root of 2 is, but this is close. So for sure that's 1. And 408. So when I subtract, I'm going to get 8 from 77 is 69, 169. Bring down to 0. I'm expecting to get the answer 4, so I'll just put that there. 4 times 408 is 1632. Subtract, I'm going to get 58. Bring down to 0. I'm expecting to get the answer 1. Subtract 408. And I'm going to get 92. Gets me to 500. So 80 plus 92, 172. Add a 0. I'm going to expect this goes into here 4 times. 4 times 408 is 1632 again. If I subtract, I'm going to get 68 plus 20, that's 88. And 88 is less than half of 408. So this does not round up to 5. And this is accurate to 3 decimal digit accuracy. So this, we were able to hand calculate the square root of 2 to 3 decimal digit accuracy. So let's quickly do one more. Let's do the square root of 3. Now I know it's approximately 1.732. I memorized that because that was the year George Washington was born, and I'm American, so if you're not American, it may not help as much, but this is how I memorized the square root of 3. So, and I know that 49 is close to 3 times as much as 16. So, for example, 7 times 4 times 7 times 4 is equal to 49 sixteenths. So this is going to be slightly more than the square root of 3. So I can put that on this side again. And I want this fraction times this fraction to exactly equal 3. So I would put 7 down here. I want to cancel 7s. And 4 goes and do 12 3 times. So if I want to find this number now, I add and divide by 2. Which is 48 plus 49 over 28 over 2, which turns out to be 97 over 56. So to find this number, we just put 97 here. And 56 goes into a certain number 3 times. It goes into 168 3 times. Now, it turns out there's a funny way to add. A lot of students mistakenly add fractions by just adding the two numerators and adding the two denominators. And that's not a good thing to do usually. But sometimes we can cheat and do it that way. So we're going to add, but I'm going to put a circle around it because it's going to be a weird kind of adding. We're just going to add the tops and add the bottoms. And what we get is called the median. Now, one property of the median is the median will be in between these two numbers on the number line. So when I find the median, it's going to be probably closer to G than either of these two. So if I add these two, I'm going to get 265 and 153. And now I'm pretty confident if I divide this into this, I'm going to get the square root of 3 to at least 3 decimal digit accuracy. In other words, it's going to be 1.732, I believe. Let's see if that works. So 153 into 265. Okay, I'm expecting to get 1. I'm going to get 1120, take away 1071. That's going to be 29 plus 2049. Bring down the 0. This we expect to go in 3 times. Because of that, 3 times 153 is 459. Subtract, we're going to get 31. Bring down a 0. We're expecting this to go in there 2 times. 2 times 153 is 306. So very close. So we successfully hand calculated the square root of 3 to 3 decimal digit accuracy. Okay, so now I'd like to briefly see if we can see a connection between the harmonic mean and Pythagorean triangles. So in a previous video, I said the harmonic mean has this little known formula. And this b minus a over b plus a, it also shows up when you're doing Pythagorean triangles. So possibly there's a connection. So for example, if we have the fraction d over m equal to 1/2. So d is 1 and m is 2. And if we plug into this formula, this will give us the hypotenuse of a Pythagorean triangle. And one leg will be m squared minus d squared, and one leg will be 2md. So in this case, we're going to get 1 squared plus 2 squared is going to be 5. 2 squared minus 1 squared is going to be 3. And 2 times m times d is going to be 2 times 2 is 4, times 1 is still 4. And we end up with the famous 3, 4, 5 right triangle. Okay, known as a Pythagorean triangle. Now, it turns out this fraction has an odd on top of the even. It's not the only fraction that gives us this result, the 3, 4, 5 right triangle. If we go ahead and do this, we write 1 here and 2 here. Now, actually I don't like 1 and 2 because that'll make the number in the middle a mixed number. So if I want a whole number here, I have to double both of these numbers. So I can go 2 and 4. If I go 2 and 4, I get 3. And 3 minus 2 is 1. That gives me the fraction 1/3. And that'll be the other fraction that gives me the same result. So suppose I have d over m being 1/3. So then I have m squared plus d squared is equal to 10, and m squared minus d squared is going to be equal to 8, and 2 times m times d is going to be equal to 6. Well, that's almost the same result, it's just everything's doubled. So now if I go ahead and divide by 2, I'm back to 5, 4, and 3, which gives me the same 3, 4, 5 right triangle. Now what if I want to go back again? I want to make a full loop. So if instead I put 1 and 3 here, and then I get 2 and I get 1. So either way, what I'm trying to say is 1 and 2 are a partner pair. With 1 and 2 together with 1 and 3 are a partner pair, because both of these fractions give you the same Pythagorean triangle. So I don't mean to say minus, I mean to say they're related. They're related fractions. They give you, notice one is an odd on top of even, the other one's an odd on top of an odd. And so every pair is going to have that. Now, instead of doing it geometrically, you can use this fraction. So b minus a over b plus a. So again, we can call this a and this b. We've done that before. So in this case, here we have 3 minus 1 on top of 3 plus 1, which is 2/4, which is 1/2. So it takes the fraction 1/3 and gives you 1/2. If you start with 1/2, you're going to go b minus a over b plus a, and you're going to get 1/3. So b minus a over b plus a, which is part of the harmonic mean, is also used for Pythagorean triangles. Again, in this formula, when we're working with the fraction d over m. So when you get a fraction, you call the top d and the bottom m. And then you use these formulas to give you the 3 sides of your right triangle. So let's look at a few examples just to make it clear. So let's start with 1/5. All right, so we can go b minus a over b plus a, which is 5 minus 1 over 5 plus 1, which is 4, 6, which is 2/3. So these two fractions are related. So again, we have odd and odd, even and odd. So every fraction has a partner. Let's do another example. Let's look at the fraction 2/3. Okay, so let's put 2 here and 3 here. Now, the middle won't be a whole number. So let's double the 2 and get 4, double the 3 and get 6. So the middle is 5, and when we subtract, we get 1. So we get the fraction 1/5. Again, we have 2 odds, and we have an even and an odd. So if you want to get all the Pythagorean triangles, you don't have to use both cases. You can stick to the case where you have an even and an odd. Okay, so this even with this odd gives you the 3, 4, 5 right triangle. This even with this odd gives you a different Pythagorean triangle. Now we're going to try to apply the harmonic mean to bargaining. So suppose you want to buy something for $2, Somebody else wants to sell it to you for $6. So you might think, well, just compromise. The middle is $4, so just buy it for $4. But what if you decide instead to have the percent increase match the absolute value of the percent decrease? Then it won't be at 4 anymore. It's not going to be at the arithmetic mean, it's going to be at the harmonic mean. So let's see if we can derive that result. This work is derived from a paper by George Polya that was published around 1950 in the American Mathematical Monthly. So let's draw this like this. We have 2 here and 6 here. And since 2 plus 6 is 8, we're going to have 8 spaces. And we know the harmonic mean is 2 spaces over. So this is going to be 2, 3, 4, 5, and 6. So when we go from here to here, we're raising 1. And we go from here to here, we're dropping 3. But when you look at percent increase and percent decrease, let's define it as follows. From here to here is a change, and from here to here is also a change. So we're going to have change over the old amount. So the change over the old amount is equal to blank per 100. Blank percent is blank per 100. So I have my students say this 3 times so they memorize it. Change over the old equal blank per 100. Change over the old equal blank per 100, and so forth. Now, so when we go from here to here, the change is 1, and the old is 2. So that's it's changed to a 50 per 100. So we go from buying something for $2 to buying something for $3. It's a 50% increase in price. When you drop from 6 to 3, the old price is 6, and the change is 3, actually negative 3, so it's a 50% decrease. We're not worrying about sign now, actually. So this is the spot where the percent increase matches the percent decrease. And this is the harmonic mean, because we have 2 and 6. We broke it into 8 spaces, because 2 plus 6 is 8, and we go 2 spaces over. So the spot is right there at the harmonic mean of 2 and 6. And if you want to find out how do you calculate the 50%, just label this as A and B. So it's B minus A over B plus A, which is 6 minus 2 over 6 plus 2, which is 4 over 8, which is 1/2, which becomes 50%. So this B minus A over B plus A goes to work again. So how do we prove this easily? We found this result. H equals A plus A times B minus A over B plus A. So if this is A, and we go to here, we're going from A to A plus A times B minus A over B plus A. So what is the change when we go from this to this? This is the change, right? It's the old plus the new makes the change. Well, actually, it's the old plus the change makes the new. So the change over the old would be this change over the old. So when we cancel, we get B minus A over B plus A. So then just change that to a percent. So it's change over the old, simplify to blank per 100. Now what about when you're going the other direction? So now the harmonic mean is also B minus B times B minus A over B plus A. So just to review, B minus A over B plus A is the length of each space. So it's saying start at B and go this far, B times. So to get here, we go 2 spaces this way or 6 spaces this way to get to the harmonic mean. So when you do this, this is the new, okay? What we want to change over the O. So this is the old, and this is the change. So it's B times B minus A over B plus A. That's the change over the old, okay? And then when you cancel, again, you get B minus A over B plus A. So either way, you're getting B minus A over B plus A. Now, here you're getting actually a minus, but I don't care about the sign. So the harmonic mean is the spot where the percent increase equals the absolute value of the percent decrease. And George Polya, when I read his article a few years ago, I don't think he knew this formula. So he proved it, but he proved it in a more difficult way. If he had known this formula, now my memory could be faulty, but if I remember correctly, he did not know these two formulas and did not prove that result so easily.